So that works.
Just check your voice.
Test 1, 2, 3. Test.
Yeah.
1, 2, 3. Okay.
What was that? We'll just check, sir. Check
Okay.
the clicker. Sorry.
Shift. No. This one?
Okay.
Wow, great. Okay. So, test. Okay. So, welcome everybody to my talk on AI methods for real-time IoT sensor stream analytics. My name is Romeo Kinsler, and I work for IBM Watson IoT. So I start also, like everybody here, with a little story, and I have to compress this talk into 15 minutes. Normally I take 30, so I will talk double speed, but I will do a recording, so you can play it at half speed if you like. So that's John. John is now at the office, and he stopped working and wants to go home. It's 6 p.m. And unfortunately, there's a lot of music going on. No, unfortunately, there's a thunderstorm going on, and IBM Watson sends him a message that there's a thunderstorm, and he recommends him to take an electric vehicle to get home, and already booked that. And he also informed his son, Jack, that now he doesn't need to use public transport. He just gets picked up by his father. So both are happy. They just drive home. But unfortunately, the story is taking place in the US, and there are occasionally tornadoes. And IBM Watson tells Jack and John, please search for shelter under a bridge, and instantly informs mother and daughter that they are safe but will arrive later, and also instantly cancels his telephone conference and reschedules it for the day after. So who of you thinks that's fiction, and who of you thinks that's possible? So do you think that's fiction? I'm very much convinced that's true in the next couple of months or years. So why do we IoT now? Last year we had 15 billion connected devices. In 2020 we will have 40 billion connected devices, and that's far more than the world's population, where India is contributing a lot. I can do jokes about Indians because I'm half Indian, struggling with that. And I think we Indians, we contribute to the quality, not to the quantity, as you have seen maybe with a 12-year-old software developer. So 90% of all data generated worldwide this year is on the edge on an IoT device, and we never capture, analyze, or action on that data. That we want to change. Even 60% of the data loses its value within milliseconds. For example, think of a connected car. If the guy before you brakes, your car should immediately brake and not wait 4 minutes until it brakes, but the accident already happened. The new generations of sensors, they are low cost, low in energy consumption, they have low data transmission cost, and they can be run on batteries for months. To give you an idea, for only $5 you get a humidity sensor. You can put that into soil. You power it with a little $2 battery and transmit the data wireless via a gateway which costs you $15. So for $100 you can deploy just a sensor and send that data to the cloud. So what IBM and other providers propose to use MQTT as the protocol for sending IoT data to the cloud. MQTT is a very lightweight telemetry protocol which supports the PubSub paradigm. Was invented by IBM in 1999 and was cast into the OASIS standard by 2013. In IBM, we have a message broker called IBM Message Site, which also comes as a client, but you don't have to care about that because we have this as a service and call it IBM Watson IoT platform together with some security and management and analytics services on top of it. Actually, you need only 3 lines of Python code to send messages from a Raspberry Pi to that broker. And we take care about load balancing, and we also take care about quality of service. We specify here the value of 2, and then we guarantee that your message is delivered, guaranteed delivered in the cloud. If you want to learn more about that, we have the first non-academic course on Coursera. You can join that, it's for free. We have more than 7,000 students at the moment. So now I've told you how to implement the central nervous system of IoT, but what is missing is the brain. So that's where my part comes in. You can do machine learning in two flavors. You can do machine learning on historic data, or you can do online learning. Online learning means you create a machine learning model via real-time sensor streaming. Both have pros and cons, but you actually have to use both of them to be successful. The state-of-the-art pipeline we have in the cloud for machine learning is based on ApacheSpark. As you can see here, we run this on 48 core machines with 3 terabytes of main memory with a 10 gigabit per second interconnect. And as you can see here, we support all the projects on top of Spark. Some are open source, some are coming from IBM. So what we do with that state-of-the-art architecture is we react on real-time data, we store it for model scoring, we do feature extraction, and we do basic machine learning. The cognitive version of it will introduce something different. It will be based on deep learning. So for those who haven't heard about deep learning, that's a new fashion of neural networks. That's, for example, a 3-layer feed-forward neural network mapping a 3-dimensional input to a 2-dimensional output. That's the topology of a single neuron by taking upstream input from other neurons, calculating a nonlinear transfer function, and putting down the result to downstream neurons. You can add additional layers in such a network, but this basically generates this further abstractions of your data. That's something we previously had to do handcrafted, so we had to introduce handcrafted features, but with those deep networks, you can actually train the network to do the feature extraction part for you. The most prominent example for such networks are convolutional neural networks, which are inspired by the visionary system of the human brain, which basically do exactly the same thing. They learn very abstract features, and the more you go up the layers, the more concrete the features are. So they are outperforming every other algorithm on the planet which is not based on deep learning. You can transfer such a neural network into a generative model and basically use the image from an artist and use any other image, and then you run gradient descent on the result, and when you hit a local minima you get something like that. That seems like to be painted from a particular artist, and I'm also not the first one doing such thing. So you can see here the Golden Gate Bridge and apply different styles running generative models on neural networks. This startup picked up this idea, and that's a startup based in Switzerland where I come from, and they are running on the IBM Cloud on the GPU cluster, and they are actually providing this as a service. And feed-forward neural network can learn any mathematical function, but it's very bad at recognizing sequences. Therefore, a neural network can be extended with reverse backpropagation connections, and even with hierarchical memory, then you get a long short-time neural network that is capable of doing wonderful things. For example, learning how to write Shakespeare by reading Shakespeare literature, or it can write mathematical publications by reading mathematical publications. It can generate C code by reading the Linux C kernel source code, and it's outperforming anomaly detection algorithms in time series analysis. So LSTM network is Turing complete, so it can learn any software you implement. You just need enough training data. The problem with neural networks are that they are very cost intensive, especially on training, but also on scoring. 2009 we had a system with 16,000 cores, and 2016 you have the same capacity in one NVIDIA GPU card. And imagine what you have 2018, we are generating ASIC application-specific integrated circuit capable of running neural networks in silico. So that actually transforms our state-of-the-art machine learning architecture with software called deep learning for J, which we accelerate using GPUs and vector units on CPUs. So that's the whole pipeline we use for IoT. We get the data from the IoT Foundation via MQTT. We cache it in Apache Kafka. We process it in ApacheSpark with MLlib and deep learning for J. The data we store in OpenStack Swift. And on top of that, we run Python notebooks. So you can see here the HR section from the conf file, the main conf file. So I just get all the dependencies, import them, and then I can actually create neural networks. And the important thing is here you can push the Spark context into such a neural network configuration, and then this neural network runs in parallel on the Spark cluster and using the GPUs on the Spark cluster. On top of that, you get all the Watson services. You get screening analytics for low latency screening. You get Twitter data, weather data, and more than 120 other services. And that's how we transform IoT to cognitive. Thank you very much.
Okay, I'm done.